The moment you tune in, well, the clock starts ticking. We all feel it, that relentless fury of time carrying us forward.
Yeah, it's probably the most intimate experience we have, isn't it? This sense of a uniform, universal flow.
Exactly. Marching steadily from past to future, same for everyone, everywhere. We just sort of take it for granted.
Like a great cosmic river, you know? The backdrop for everything. We assume the time right here, by your microphone, is precisely the same as time on, say, the far side of the galaxy.
But here's the kicker. According to modern physics, we're talking relativity, quantum mechanics, that whole common sense picture, it's fundamentally wrong.
It really is. It's just a crude approximation.
Like thinking the Earth is flat, maybe. Useful day to day.
Exactly, an error of perspective. Or thinking the sun goes around us, works locally, fails globally. So our mission in this deep dive is to really explore this disintegration of time.
Right, how physics just tears down everything we thought we knew.
And then the really fascinating part, how our familiar sense of flowing time somehow manages to, well, to emerge back into our world.
Okay, let's dive in.
Yeah.
Pillar 1. The loss of time's uniformity. We assumed clocks tick the same everywhere.
Yeah.
But you're saying,
Nope. Demonstrably false. Time does not flow at the same rate everywhere. And this isn't just theory anymore.
it's measurable.
Oh yeah, it's an engineering fact now. Time runs faster up on a mountain and slower down on the plain.
And we're not talking like near black holes or something extreme.
Not at all. We
Well-
can measure this difference with high-precision atomic clocks.
Yeah.
Even over just a few centimeters. Seriously. Put a clock on the floor.
Uh-huh.
It will run infinitesimally slower, but measurably slower than the identical clock you put on the table just above it.
Wow. Okay. Is there a practical?
Yeah.
Why should you care about this tiny difference?
Well, think about your GPS. The only reason it works accurately
Right.
is because engineers have to account for this. Time flows slightly differently for the satellites orbiting Earth. They're higher up in weaker gravity.
So time runs faster for them.
Slower, actually, because of their speed, but faster because of the weaker gravity. The gravity effect dominates for GPS. If they didn't correct for this relativistic effect,
Right.
your GPS position would drift off by kilometers every single day. That's general relativity in action right in your pocket. It proves time is, well, local to you.
Okay, that completely shatters the old Newtonian idea, the fixed container of space and time.
It does.
So mass isn't just pulling things. It's actually warping space-time itself.
That's the insight. Mass and energy curve space-time.
But why does that warping make things fall towards slower time? That seems weird.
It does sound weird, but think of it like this. Objects naturally follow the path of, let's say, least resistance through space-time. Technically, it's the path of maximum proper time elapsed between 2 points in their journey. So when you throw a ball, it's not really being pulled down by a force in the old sense. It's naturally following the curve in space-time towards the region where time is running slower near the Earth's mass. That's just the most efficient path for it to take through this warped geometry.
So no universal clock ticking away, just
Right.
countless local proper times,
Oh.
all slightly different depending on gravity and motion.
Precisely. A whole network of them. Time has lost its universal uniqueness.
Okay, pillar 1 down.
And that leads us right into the second lost pillar, the direction of time, the arrow.
Right, this one feels even more fundamental. We know time has a direction, causes come before effects.
You drop a glass, it shatters, it doesn't spontaneously fly back together.
Exactly, the past feels fixed, done, we remember it, the future feels open, unwritten. How can that not be fundamental?
Well, here's the really bizarre thing. If you look at the basic laws of physics, Newton's laws, Maxwell's equations for electricity and magnetism, even Einstein's relativity and quantum mechanics, they are all essentially time symmetrical. They work just as well forwards as backwards in time.
What do you mean? Like if you film billiard balls colliding?
Right. Film that, then run the film backwards. The reversed sequence of events. It still perfectly obeys the laws of physics. The equations don't inherently distinguish between past and future at that fundamental level.
But we clearly do. Our whole experience screams directionality.
Yeah.
So if the fundamental laws don't see an arrow, why do we? What's the exception?
The exception. It comes not from the fundamental laws governing individual particles, but from the statistics of vast numbers of them. It comes from thermodynamics.
Heat and energy,
Specifically, the second law of thermodynamics, the principle of entropy.
which basically says disorder increases, things tend to run down.
That's the gist of it. Heat spontaneously flows from hot things to cold things, never the other way around. A drop of ink spreads out in water. It doesn't gather itself back into a drop. This constant, irreversible increase in disorder or entropy. That is the only physical law we know that points a clear direction in time.
Okay, so entropy gives us the arrow. But didn't Boltzmann link entropy to us, to how we look at the world?
Exactly. This is where it gets really mind-bending. Ludwig Boltzmann's genius was showing that entropy, this disorder, isn't necessarily an intrinsic property of the microscopic world itself.
It's what then?
It exists because we describe the world in an unfocused, approximate, macroscopic way. We talk about temperature and pressure of a gas, not the exact position and velocity of every single molecule.
Right, we ignore the details.
And Boltzmann showed that if you could track every single microscopic detail, the mathematical distinction between past and future would largely vanish. The increase in entropy is tied to this coarse graining, this blurring of our vision.
Hang on, you're saying the only reason time seems to flow forwards is because we're sort of squinting? Because we ignore most of reality's details. That feels, I don't know, like a demotion for time's arrow.
It's tied to our scale, our interaction with the world. The flow of time is, in a deep sense, a statistical effect, an emergent property of how we, as macroscopic systems, perceive things.
So why does it flow this way, from past to future?
Because the universe, relative to our blurred perspective, started in a very, very special, highly ordered, low-entropy state. And everything that happens, life, evolution, stars burning, everything is just the universe moving from that improbable, organized past towards a much more probable, mixed-up, disordered, high-entropy future.
Wow, okay. So time's arrow is a consequence of our fuzzy view and a special starting point. Let's move to the third collapse then, the end of the present, the universal now.
Right. If time depends on where you are due to gravity.
Pillar one.
And it also depends on how fast you're moving.
Which it does, right. Speed slows time down too.
Absolutely. That's special relativity, measured since the 1960s, flying atomic clocks on jets. The faster you move, the slower your time passes relative to someone stationary.
So if time depends on location and speed, what does that do to the idea of now across large distances?
It completely destroys it. The idea of a universal now is an illusion. Think about, say, your sister on Proxima b, 4 light years away. If you ask, what is she doing right now? That question is physically meaningless.
Because light takes 4 years to get from her to me, and vice versa.
Exactly. When you look through a telescope, you see her as she was 4 years ago. If you send her a message, she won't get it for 4 years. There's simply no way to establish a shared, instantaneous now between you.
My now is here, her now is there, and they're disconnected.
Precisely. The concept of simultaneity is relative. What one observer considers now across a distance, another observer moving differently will see as happening in the past or future.
So what's the structure then, if not a single line of time?
It's what physicists call a partial order. Think of it in terms of cause and effect, limited by the speed of light. From any event, like you snapping your fingers right now, there's a light cone stretching into the future, all the events you could possibly influence. And there's a light cone stretching into the past, all the events that could have influenced you.
Okay. Past, future. What's left?
Everything else. A vast region outside your past and future light cones. This is sometimes called the extended present or elsewhere. Events happening there are causally disconnected from your now.
So for someone on Proxima b, their now could be in my extended present?
Yes. And depending on relative motion, their now might correspond to what you'd consider hours, days, even years in your past or future if you tried to synchronize. The present of the universe as a single slice in time just doesn't exist.
Mind blown. Okay. Relativity kills the universal clock and the universal now.
Yeah.
What happens when we throw quantum mechanics into the mix? This feels like the final nail on the coffin.
It kind of is. When we try to combine gravity, Einstein's theory of space-time, with quantum mechanics, which governs the very small, well, things get even weirder. We're talking quantum gravity.
And what does quantum gravity do to time?
It suggests a fourth loss, the loss of continuity. Time isn't a smooth, continuously flowing river at the most fundamental level.
It's choppy, grainy.
Exactly. It's likely quantized, just like energy comes in discrete packets called quanta.
Right, photons.
Time itself might come in indivisible minimum units. There might be a smallest possible interval of time.
Is there a scale for that?
Yes, the Planck time. It's incredibly, unbelievably small, about 10 to the minus 44 seconds, 10 euros. Below that scale, the very concept of time, of duration, probably breaks down entirely. It ceases to have meaning.
So you can't keep dividing time forever. It hits a floor.
That's the idea. Space-time itself, at that scale, is thought to be a sort of quantum foam, fluctuating, uncertain.
If time itself isn't continuous, what does that imply about, well, about things, about reality?
It pushes us towards thinking that the world isn't fundamentally made of things that last through time, like a stone enduring moment after moment.
What is it made of then?
Events, processes, happenings. Think of a kiss or a storm or a collision. These are inherently temporary processes limited in space and time.
So even a stone isn't really a thing.
Not fundamentally. A stone is more like a complex dance, a temporary equilibrium of underlying quantum fields, constantly vibrating, interacting, changing just very, very slowly from our perspective. So this quantum granularity really emphasizes the ubiquity of impermanence. Change is fundamental.
Okay, let's recap the demolition job. Time is local, not universal, pillar 1. It doesn't have a fundamental direction that's emergent, pillar 2. There's no universal now, pillar 3. And it's not even continuous, it's granular, pillar 4.
Pretty much. We've stripped away all its intuitive properties.
Which leads to the biggest question. If time isn't fundamental, and you mentioned the main equation of quantum gravity, the Wheeler-DeWitt equation, literally doesn't have a T for time in it,
Yeah.
then how does anything happen? What does that timeless reality look like?
Well, the equations of quantum gravity describe a world, but it's a world of relationships. It's a network of events where variables describing the universe change relative to each other.
Not against some background clock.
Exactly. Think about change. Does the position of a pendulum bob change because time t increases, or does t increase because the pendulum bob moved? The equations just relate the variables, the bob's position, the Earth's rotation, the decay of an atom directly to each other.
I heard an analogy once, comparing Singapore, driven by a master clock schedule, to Naples, where things happen based on local dependencies. The shop opens when the owner arrives, who depends on the fisherman, who depends on the tide.
That's a fantastic analogy, yes. The fundamental description might be more like Naples, a web of relative change, correlations between variables, without needing a master metronome ticking T for the whole cosmos. Change is everywhere, it's just fundamentally relative.
So if the base reality is this timeless network of relations, how on earth do we get back our experience? The feeling of flow, the arrow, the ticking clock. You said before, time is ignorance.
It comes back to that unfocused view, our coarse graining, because we, as complex physical systems, humans, measuring devices, whatever, can only interact with and process a tiny, tiny fraction of the universe's microscopic variables.
We're effectively blind to most of the detail.
Massively blind. And it's this very act of averaging, of looking at macroscopic states, temperature, pressure, things we can perceive and measure that allows time to reemerge.
How did that work? How does ignorance create time?
When you apply the tools of thermodynamics and statistical mechanics to these macroscopic states, states defined by our ignorance of the microdetails, a parameter naturally pops out of the math. And this parameter behaves exactly like time.
What's it called?
It's often called thermal time. It relates to temperature and the flow of heat, and it tracks how these macroscopic states evolve. It emerges purely from the statistical description of the system when you ignore the underlying microscopic frenzy.
So let me see if I've got this. The fact that the sky seems to rotate daily isn't fundamental about the sky. It's because we are on a rotating Earth. It's a perspective effect.
Right.
And you're saying the seemingly fundamental flow of time from past to future, the basis of memory, life, consciousness, that might also be a perspective effect.
A perspective effect arising from the specific way we interact with the universe, the drastic unfocusing inherent in our macroscopic nature.
And linked to that low-entropy past.
Yes. The arrow of time, the very flow we experience, seems to exist because we are physical systems interacting with the world through variables that, relative to us, define a past state that looks remarkably ordered. Low entropy. It might not be that the universe's fundamental state had an arrow, but that our particular way of carving up reality creates one.
That's profound. We create time by ignoring reality's details.
In a manner of speaking, yes. Time emerges where physical systems interact in a way that defines a low-entropy past relative to those systems. That's where memory, life, and our experience of flow can happen.
Okay, this has been an incredible journey through the breakdown and sort of reconstruction of time. Let's try to synthesize this for everyone listening.
Sure. So the takeaway is, time isn't that simple, uniform river you thought it was. It's local, different for you than for someone on a mountain or moving fast. Your GPS proves this every day.
It's also likely granular, not smooth, breaking down at the tiniest Planck scale.
Right, and fundamentally it seems to be relational, describing how events change relative to each other, not flowing independently.
And perhaps most strikingly, its direction, the arrow from past to future, isn't fundamental either. It emerges from thermodynamics, from entropy.
Which itself seems linked to our macroscopic, blurred perspective on the universe, and the fact that the universe looked very ordered in the past relative to us. Time is, in a deep sense, a product of our ignorance.
It really puts our human experience in a different light. It makes me think of that famous Einstein quote, the one about the distinction between past, present, and future being a stubbornly persistent illusion. And the context makes it even more powerful. He wrote that in a letter of condolence to the family of his lifelong friend, Michel Besso, just after Besso died.
Exactly. It wasn't just an abstract physics statement. It was him grappling with loss, with the meaning of time in the face of human mortality. It shows how deeply this physics connects to our emotions, our sense of being.
It really underscores that idea of impermanence you mentioned earlier. If the fundamental reality is events, not things.
Then change truly is the only constant. The cosmos itself is telling us that.
Okay, to leave you, our listener, with one final provocative thought that kind of ties all this together, think about energy. We're always talking about needing more energy, finding new sources to power our world, our economies, our growth.
But physics tells us energy is conserved. The total amount in the universe doesn't really change, it just transforms.
So if energy isn't being used up, what really drives everything? Why do engines run? Why do we live and grow? Why do things happen?
It's not the energy itself, it's the consumption of low entropy.
Disorder increasing. That's the real currency.
That's the real scarcity, the real driving force. Think of the sun. It doesn't just send us energy, it sends us highly organized, low entropy energy in the form of hot, focused photons.
And we use that ordered energy.
We use that order to build complexity, to power life, to run machines. And in the process, we inevitably degrade that order, radiating less organized high-entropy heat, older photons, back out into space. The universe runs on the continuous degradation of order, the flow from low entropy to high entropy.
So that constant running down, that increase in disorder, that is the engine of change. And that's intimately tied to the emergence of the very flow of time we experience.
Precisely. The universe isn't driven by energy, but by the availability and consumption of order, of low entropy. And that consumption is the process that manifests to us as the passage of time.